Welcome everybody here to the last in the series of the Advanced Transportation Technology Seminar Series. I want to, yours is not on yet. We'll turn it on in a minute, okay? We are very fortunate to have Nicholas Giudice here, who is Giudice, sorry, to speak to us today. I just wanted to make some very quick announcements. This is the last in the series. The classes are ending. And so for the students who are signed up for credit, you will have an evaluation form. And because this is a seminar series, we've created a few questions that we'd like everybody who's taking this course for credit to answer. So on the form, you answer those on the back. So those of you who are taking for credit know who you are. And when it asks you what did the instructor do that most helped your learning, I would suggest that you, what did the speakers do to help you with your learning? So this is a seminar, it's not your regular kind of course. So adapt the evaluation form to the nature of the course. So, and by the way, all of you are filling out the form. Should turn, you're all here in the classroom, you should turn your form in. You want to raise your hand? Why don't you give it to he's one of the students, and he will bring it to Jeannie Sitzman here in mechanical engineering. So none of us, and myself included, will ever touch the form to make sure that it is objective and unbiased in every way, shape, and form. Anyway, let me introduce our speaker today. Nicholas originally came from Connecticut, got his undergraduate degrees in Rhode Island, and then joined the University of Minnesota and worked with Professor Gordon Legg in the psychology department. After he received his PhD in 2005, I'm sorry. 2004, okay, we want to get that right. He did a postdoc at the University of California at Santa Barbara, and then joined the University of Maine in Orono in 2008. So he's been there for 3 years, and he tells me some interesting things about Orono, but I'm going to let him, I don't want to take too much of your time. I'm going to let Nicholas speak. We've agreed that at 50 minutes, I will tell him that we've reached 50 minutes so that he can close up, because normally I can do some hand signals or something, but I can't do that in this situation. So I'm just letting you all know that at 50 minutes, I'm going to tell him that we've reached 50 minutes. Okay, without further ado, let's turn your mic on. It's now on, and it's your show.
Thank you, Max. And you certainly can give hand signals. I just probably won't listen to them. So don't remember your evaluations are based on the whole lecture series, not just mine. So I feel a little bit of pressure here. So it's great to be back in Minnesota. I feel like I've been here long enough to know that I should not have. It's December here, and I, for some reason, showed up with no gloves, no hat. My mistake. Anyway, this talk differs a little bit from my normal talks in that I've decided to focus less on data from my particular projects and to talk kind of at a high level about current and future navigation problems, especially relating to aging and low vision and low vision in general. So much of what I'll be discussing will be, at least in the first half of the talk, will likely be familiar to a lot of you transportation folks. But I'm coming from an experimental psychology and kind of as an HCI person now, so hopefully I'll bring a little bit of a different perspective. And then the second part, I'm going to talk about some of the work that I'm doing on interface design and indoor navigation. All right, next. So this figure, as you know, is the Minneapolis Skyway system, or at least a part of it. And so I ask you to imagine that you need to get from, say, the target center to, let's say, the government center through the Skyway system. And so my question to you is, I guess, what information would you use to perform this task? And it turns out that it's actually kind of a hard question to answer. Getting from place to place is a fundamental part of human behavior, and we do this every day, and it's a big part of our independence. But rarely do we actually think about what information we're using to do it. And I think that most of us would agree that we're certainly, vision's playing an important role in this process, and the notion of trying to navigate the skyway system without vision is pretty daunting. For most people, some would say impossible. And obviously it's not impossible, because I've navigated the skyway system, and plenty of people that don't see also have done it. But it requires use of different types of information. So paying attention to things like sound from the environment, texture under your feet, smell, maybe other types of things that are different from traditional sources of information like signage and color and the like. So in other words, I guess what I want to get across here is that much of the information which is important for blind navigation is often never even consciously considered by sighted navigators. And a good example is, think about crossing a road. If you're at an intersection, you want to cross the road, you don't generally think of, worry about, are you going to veer as you cross the road and go out into traffic? You just pick your line and you decide where you're going to walk, and you walk there. But this is a big issue for a lot of sighted blind navigation and people that have low vision. And it's a significantly, it's a dangerous problem, because if you veer out into traffic, obviously there's bad things happen. So this perceptual disconnect is a big reason why, or at least I argue, it's a big reason why so many accessibility issues still exist, and why solutions are often not implemented. And there's also issues of expense, and these come up. But I think a lack of understanding and awareness is a big issue here. So my take-home message, although I think it's a positive one, even though I'm going to be talking about problems, the positive part is that a lot of the things that are the most important, I think, are also the most simple to implement. And so that's a good thing in terms of promoting safety and promoting independent travel. All right. Let's move on. I realize I think I planned for an hour, not 50 minutes. I'm going to need to cut myself. Anyway, so why care about blind and low vision navigation? Well, I can speak for myself. I think some of these things are generalizable. Obviously, I have a personal interest in this, being that I do it daily. I also really believe that one's phenomenology is really a great starting point for one's science in a lot of cases, and certainly that's been true for me. I have a professional interest here in that my basic research program deals with how we represent space in the brain and how we use different senses to do this. And so studying multimodal interfaces and multimodal navigation systems is a natural application of this. I think there's also, for me, there's a big motivation that there's a growing societal concern and a growing societal need due to aging, which we're going to talk about, which has had far too, not enough research, not enough technology development, and so this is an interest to me. What about some blindness facts? So, every 7 minutes, somebody in the U.S. becomes blind or low vision, right? So that means that, within the range of this talk, depending on how long I go, 7, 8 people this will happen to. 12 million people in the U.S. have some form of uncorrected vision loss, with 3.4 million being legally blind. And a note here on terminology. These stats you see used in lots of different ways. So legal blindness is essentially, the definition is that vision in the best vision in the uncorrected eye of 20/200. So essentially, what I would see at 20 feet, you would see at 200, or field loss of under 20 degrees. Low vision is often 20/60. It's a little bit confusing, though, because most people that are legally blind have some vision. So a lot of people think that when you say legally blind, people are seeing dark. That's really only about 5% of the population. And the rest of them are often called low vision, even though they don't technically fit the definition that I just gave you. So some confusion here. Really, the bigger issue with blindness is that the incidence of blindness is sharply increasing with the aging of our baby boomers. So age-related vision loss is by far the fastest growing base of our population. So current numbers that we just talked about are predicted to double by 2030. Depending on what you read, 2030 seems to be a pretty good estimate. So next slide. This means that essentially 24 million people will have some form of uncorrected vision problem in the next 20 years. So that's, this is a pretty big deal. This is everyone living essentially in the states of Minnesota, Iowa, Wisconsin, and Michigan suddenly having a vision problem. And many of these people are going to have associated navigation problems, as we're going to talk about. All right, next. This figure is just showing some current estimates and 2020 estimates of the types of age-related vision loss, the different types of etiology that cause these types of loss. Next. So how does this relate to navigation and transportation? There's lots of ways. So this is a figure of a part of Heathrow Airport. And there's many challenges with airport navigation. I think probably anyone here that's been in an airport has experienced. It's a particularly big problem for aging and low vision folks because information is almost always on these overhead signs and monitors and kiosks, which are usually really heavy in information density. They're usually very busy, very cluttered, and you usually need to read them in a rush. And these are all things that are very difficult for an older person, situations that are hard to read. Gordon could speak to research on lots of this. It's also, these types of displays are not possible for a blind person to access, so that's obviously a problem. So again, if you had to navigate from this, in this figure, going from the check-in to the upper level, how would you do it? It's even just finding the queue is often difficult if you can't see where the queue is. So there's lots of these kind of things that you often may not think about that would be, or things that are important or difficult for a blind person. So outside, you have a lot of similar issues, but the problem is often not as big a deal, at least in a lot of certain types of cases, because we have GPS guidance, we have accessible GPSs that work pretty well. There's lots of other cues about environmental identification and detect warnings and things, and as we'll see, they're not always perfect, but they're there, and these things are often not there inside. So I don't have the answer here. I wish I did, because I probably could get a lot of grants, but I think it's a worthy problem to consider. I know it's a worthy problem to consider, and I think so these are some of the issues that are worth thinking about. And I'll talk about some preliminary solutions that at least I'm thinking about at the end here. But the bottom line is that I think we're woefully unprepared to meet the navigation problems of the fastest growing base of our population with our current technology and our current installation base of accessible information, environmental information. This is both a public and a private sector issue. All right, next. So environments like skyways, airports, malls, all these types of things, lots of others, can be, obviously are difficult to navigate without vision. But as I said, they certainly can be done. But I don't think it's terribly surprising that for many individuals doing this, this experience really high levels of stress, really high levels of anxiety in terms of traveling alone in these types of places. And this is not kind of an isolated problem. This is a real problem. It's been estimated that up to 30% of blind people don't actually travel independently outside of their homes. I think this number is changing somewhat because of technology and because there is a growing installation base. But it's still a large percentage of people compared to sighted people. And this, obvious negative consequences. You think about the educational, vocational, social consequences of that are lost by not traveling independently. I think it's a big example of why 75% of this demographic is unemployed. Okay, so now we're beginning to see a lot of these similar problems with older folks. As people age, they're also starting to lose their independence. Their vision's going. They fear traveling alone. They're worried about getting lost. You stop being able to see signs and landmarks. So a lot of the same issues. And it makes sense, especially for an aging person. You've had sight your whole life, and suddenly you're starting to lose your sight, and you can imagine that it's stressful, and people's quality of life certainly goes down. Okay, so what do we do? What's the solution here? And I guess once again, I don't really have the answer, although I think part of the solution is better understanding of some of the problems. Next. There's lots of problems. Two major ones that are associated with, particularly with age-related vision loss, are driving and falling. And you know, diseases like cataracts, glaucoma, and AMD often alter older people's depth perception, the visual acuity, the center or central or peripheral field loss. Depends on the particular condition. But there's lots of conditions that happen that lead to many of these types of problems. And so some of these things are being dealt with optically, but many of them require better awareness and better access to environmental cues, and that's where I think we're really kind of falling short. So some disturbing driving stats here. And I think someone gave a talk in driving in this lecture earlier, so they probably went over a lot of these. But currently, drivers over 85 have 4 times more fatal crashes than teenagers, which is pretty scary because when I was a teenager, I think I was in 4 crashes with friends. I wasn't driving, actually, but I was driving a couple times, but we didn't crash. People over 65 were responsible for about 11% of fatal crashes in 2005. This is estimated to skyrocket to 25% in 2030. So this big picture is pretty clear here. I don't do driving research yet. It seems like something that I would think about certainly as a growing problem. But this is probably the most studied area of aging in navigation, certainly more than the kind of skyway walking, airport walking situations that we talked about earlier. Some disturbing falling stats. So you can see some of these, but 1 out of 3 adults over age 65 fall each year. Over 19,000 elders died from unintentional falls each year. 2.2 million go to the hospital because of falls. And direct medical costs because of falls are estimated over $28 billion. That's a lot of money. Next. All right, so I started with saying simple solutions, so the best solutions are often the simplest solutions, and I'll stick by that. Technical improvements, technological improvements, high-tech research is important. I do this type of research. I like it, but at the end of the day, something simple like white lines on a curb probably prevent more injuries than anything else. And so I believe the main challenge for independent blind navigation is really one of information access. It's a problem of information access. It's not really a problem of vision loss. And so the goal for designers, for engineers, for people that are working in this domain is to improve access by improving, providing access to more environmental information that supports safe and efficient travel. Okay, so how do we, that's easy to say. What information should be provided? So information requirements are supporting navigation is a big topic in spatial cognition research, which is the area that I'm coming from, in other areas too. It's not fully known, but there's certainly some good examples of what does work, and especially in the context that we're talking about. So problem 1, though, that I think is first we need to solve is that designers, engineers, facility management people, planners, a lot of people are just hammered with standards, guidelines, regulations, these things. You need to do this. And there's no underlying rationale of why these things are important. There's no explanation for why to do that. So people see a guideline as something that often seems kind of silly. It's onerous. If there's compliance, it's often because of legal reasons, not because of understanding that why this makes a difference to a particular set of users. So I think this is a bad starting point. And the problem here is a disconnect between the researchers, engineers, and end users. And it's an easy problem to solve. Easy may be an oversimplification, but there is a clear solution. So one part of this solution is policy level. There needs to be better explanation of why guidelines are important to the end user in the documentation. This should be made clear. A best approach, I think, though, is if you're working on a project and you're dealing with something that's involving adding environmental cues. Try immersing yourself in the situation. So think about the solution by experiencing the problem yourself. So try detecting a curb while blindfolded. Try crossing a street using an APS or pedestrian signalization. Oftentimes you don't really think about the issue until you actually do it. And another approach is to watch potential users doing the task. So look at what problems they're actually facing. I do this a lot with people in my HCI class. You get programmers. Programmers never think their code is bad, and they'll fight with you to the end. But if you have them watch 10 people have problems with the interface, they may say they're all stupid, but they can't deny that it's happening. At some point, the data speaks for itself. And a lot of people just say, yeah, I was too close to the issue. I never thought of it. I think this is probably one of the best and most important ways to solve a lot of these access implementation issues. Next. Problem 2 is a misconception that expensive modifications and accessibility solutions have little utility beyond kind of a limited population base, just kind of special populations. I think the solution here is really a shift in mindset and looking at the data. So principles of universal design are relevant here. And essentially this is saying what helps one group often helps many other groups. And it has clear functional benefit, and it has clear economic advantage for all involved. And I think a good example of this, again, coming out of kind of software, but the logic is the same. So something like Apple. So Apple spends a ton of money on usability, but they put a lot of things in their products like VoiceOver, which is something that's used for blind people. But it turns out that a lot of people like using VoiceOver for editing, for reviewing, people that are dyslexic, people that have English as a second language. So it's something that they put in for one group, and it works for a lot of groups. Universal design is really the kind of just smart design, in my opinion. And I'll give some examples of this. But if you are doing this, the biggest bang for your buck, if you're doing new implementation, both in terms of money, both in terms of user function, is try to, rule of thumb, I guess, that I use is use redundant information sources. So try to be as redundant as possible when you're specifying a queue, and use multimodal information access when possible. And you'll see some of these in these next examples. Next. Okay, so I'm going to go through some practical kind of examples of good universal design and show some bad examples as well. Most are simple to implement. So this is just talking about white lines. I'm a big fan of white lines. Put white lines on steps. You can put them on platforms, on railways, and what have you. This figure shows a whole bunch of them. Yeah, this is good. The users here, this is good for people with low vision. It's really good for people that are aging. It's good for anyone navigating at night. It's good for people that are distracted walking on your cell phone. You don't just crash on your cell phone in your car. You trip downstairs. Having white lines is something that gets your attention. So tips here, make them high contrast. The goal is to get the attention of the user, to make them noticeable, to make them highly salient. So I've been in this fight with this guy in my university because he doesn't like the lines because they're too contrasty. They're too bright. I told him that's the point. Low contrast steps, for example, are one of the biggest reasons why people fall. You have cement steps and a cement walkway. People don't even see it. You have cement benches. Gordon and I have talked about this. There's these cement benches around Elliott. I don't know if they're still there. Terribly low contrast. I don't know how many times I whacked my shin on those things because I have a very little bit of vision, but you couldn't see them. All right, use high contrast lines. That's an easy one. Next. Tactile crossing or warning indicators. So these are things that you have on roads, on bike paths, and the like. Sometimes they're mixed with white lines. And these are important warnings because they provide information about dangerous transitions, so which are often very hard to perceive without vision. The best example of these were these bike paths, and I should have put a picture here, but at UC Santa Barbara, where I was at, everyone rides bikes, and they have these paths that go all around campus. And it's essentially a highway, but you can't hear it. And people go fast, and they cut across all the paths. If you walk out into the bike path, you get mowed down. So they have these detectors on most of them. And it's amazing. I mean, I taught the dog to stop there, but I would feel them. And it was the only way that I would know that I was going to go out into this bike path. And this is true a lot of times for roads. If there's ramps, which I'm going to say are a good thing, yeah, that's true. But if you don't detect the ramp, you have no idea that you're going into the road unless you hit the detectable warning. This figure shows a bunch of them. So it's good for alerting blind people, but again, it's also good for anybody who's distracted. My friend Dan, he was a professor out there. He was sighted. He could tell me how many times the warning stopped him from going to the bike path. High contrast, again, often you'll see just cement bumps. Chen-Fu and I saw some even on the way over here. I'm happy there's bumps, but there's cement, so there's no contrast. Make them wide enough. If you make them only 1 foot, then when you step, you just step right over them. You have no idea they're there. So at that point, you may as well not put them there. And another thing that's really important is you can, if you use different material surface, if it's different from the surround, then when you're tapping with your cane or with your foot or the dog or or what have you, you hear a difference, and that difference is, again, it's a redundant cue, but it's one of the best things that cues you to you're at something, and then you realize, oh yeah, there's the bumps. So again, you can try this blindfold. These things are in a lot of places in Minneapolis. Next. These are various types of curb cuts. They have various colors and textures and contrasts. But again, these are providing a smooth transition between, say, a sidewalk and a street, and they also provide orientation information, which a lot of people don't think about. So users here, it's good for people in wheelchairs, but a curb cut's great for anyone with a stroller, luggage, elderly, particularly good. So there's often an argument that these things are expensive to put in, but go back to the 28 billion in falls. Having curb cuts can make a big difference in helping with that. Some tips: consider placement of orientation of the ramp. So it should direct the user into the correct crossing trajectory. So it should kind of show them where they should cross. So if you look at these examples here, I don't know if you see that there's some problems. So the figure on the left, hopefully I've marked these correctly, is a bad example. It's a diagonal curb cut, and this doesn't lead you to a crosswalk. So if you don't know anything about the street and you go to this curb cut and you line up, you're just going to wander right out into traffic, which is often a bad plan. The figure in the middle there, it's a diagonal, which is great, but then it has a grade at the bottom. So that's great if you're in a walker or a wheelchair. That's just bad design. Figure on the right, there's our happy curb cut. That's a good one. Good contrast, has texture, has good orientation. But yeah, consider the orientation. That's something that's really important if you don't know anything about the intersection. Next. Room signs. I think I'm just going to go past this. Room signs, high contrast. The advantage here, especially for older people, and again, Gordon can tell you more about these types of things, but the one on the left has a light background and dark letters, and in a lot of cases you want to have reverse polarity, especially for older people. So you want to have dark backgrounds and light letters just because of things like light scatter, which is problematic for a lot of age-related etiologies. Also, I'm a big fan of Braille signs, but maybe 5%, around 5% of people read Braille. So having embossed letters is often just as good. I often just read the embossed, numerals. It's faster. Next. So this is the problem that I'm calling the engineering trap. And it happens when solutions are often based on kind of the intuition of a problem by the designer using standard engineering principles. Maybe a little vague, but the problem here is that you get results that often have little functional utility to the user in daily challenges. There's a few ways around this. So first, identify the problem faced by the user. Don't fabricate the problem. Figure out if it actually is a problem. This is true a lot in mobility technologies. You get people for years that have been determined to use cool sonar algorithms and different types of algorithms for obstacle detection, and some of them are neat, but they're not adopted because the cane and the guide dog do the same thing, and people don't want another learning curve and another thing to carry. So it's just it's a solution for a problem that's not really there. Assess the user needs. So intuition is not sufficient. Conduct focus groups. Figure out what people actually need to do. Chen-Fu and I were talking about this, and he's been doing a lot of this and agrees how important this is to to really figure out what the problems are. Also, consider whether your implementation makes sense based on human information processing capabilities. So a big issue in a lot of things is this failure to understand human perceptual and cognitive factors. And this can lead to some truly spectacularly bad designs. And it's often not really the fault of anyone. It's just if you're integrating auditory displays, haptic displays into into systems that are traditionally visual, people don't have knowledge of those sensory systems, and so it's easy to make mistakes. So what happens? Well, look at the next slide here. So you want to make a tactile map. A lot of people want to make tactile maps, and they want to be, try to provide access. So we say, here's a map of Minneapolis, and you say, great, I'll make that. I'll make a tactile map of that, and you do some sort of transform where you take all the visual information and make it into some tactile form. It's going to be crap. No one's going to be able to read it. It's going to be very busy. The information bandwidth of touch is something like 500 times lower than for vision. So you have to have some smart downsampling algorithm. You have to have some way to say, what is the critical information that we need? Okay, next. Accessible pedestrian signals. And I know that some people in here have done work with these. I think what gets lost a lot in the arguments about these APS are the legality of them, the cost of them, and people don't think about what information is actually being provided. So an APS is not just giving you information about is the red, the light red or green, which people can often tell without such signals, but they're providing a lot of important information about the intersection and where to walk. And this is often very hard information to get without vision. Again, this is something like the veering that you may not think about. But so the goal here is to try to match the information from the signal with the correct intended behavior of the user. So the left figure here is a push button. It has a directional vibrotactile arrow. So I like these things. So the arrow vibrates, so it's unintrusive, and it tells you, it points in the direction that you should walk. The one on the right also adds a little auditory tone, so you have some auditory way to find the signal. The center one shows an angled crossing. So again, if you come up to a crossing and you have no idea of the configuration of the intersection, well, this type of arrow is going to be really useful because it's going to say, this is the orientation that you want to line up before you cross. But the arrow should point you along the crosswalk, assuming there is one, or the expected course of action. We had this great one in Santa Barbara where they put it up. But again, they didn't understand what it was used for. So the arrow, they figured, okay, we'll put the button on there. But the arrow pointed actually away from the street. So if you followed it, you would have wandered off into someone's yard. So that's obviously not a helpful signal. The next one. This figure is an APS that provides, and I think this is absolutely the best, but they're rarely used. It's providing tactile information about the geometry of the intersection. So I didn't write everything down here. I think there's a bike lane on this crossing. There's an island. There's a rail line. There's whatever else. And islands are particularly scary. There's a lot of streets with islands. You might have a detectable warning that tells you that it's there, hopefully, but a lot of times it's smooth. There's a ramp. So if you're crossing, if you can't see the island, you'll just trundle right across it out into the next lane. So it's very dangerous. If you have this information on the box, you can feel this little map. You can build, you have knowledge of what's there, and then you can act accordingly. So this is a very important thing to have, and I think not a very difficult, this is a low-tech thing to add if it could figure out how to produce this in a way that was easy to be widely distributed. Very useful. Next. Okay, so now I'm going to talk a little bit about some of the theory that motivates some of the work that I'm doing, because I think it provides some important rationale for why I think non-visual navigation interfaces can actually work. And I'll discuss those interfaces at the end. So my basic research is part of what I call multimodal spatial cognition, which essentially refers to how we learn about space, how we represent space in our memories, how we act in space, using different information processing channels. So using audition, using touch, using vision, using language. And spatial cognition research is traditionally focuses pretty much on vision. And in a lot of ways that makes sense. Vision is the most spatial of our senses, has the largest field of view. That's not technically true. You can hear all around you with hearing, but the depth of view is quite large. It's the most bandwidth. It's parallel processing. There's a lot of, vision is an amazing source of spatial information. But what people forget is that all of our senses encode spatial information. And I kind of think of spatial information as this common denominator between the senses. And there's other common denominators. Time is another. So I argue that the majority of what most people are considering visual information is really spatial information. So if you look around the room that we're in here and just look at what are you seeing? How much of what you're perceiving visually is intrinsically visual? Color is. You could argue that aspects of texture are, though it's arguable. But think about the 3D structure of the room. Think about the relations of the edges, the surfaces, the distance and directions of objects. These things aren't vision. Vision's a conduit of these things. But they can also be specified through other sources. So that's next. So the theory is that spatial information from different senses builds up into a common representation in the brain. All right, and I believe that it's an amodal so it's kind of an amodal spatial representation that doesn't necessarily tie back to the input source. We could argue about that, but that's not the point of this talk. What's important is that this representation functions equivalently, or this is what we're arguing, functions equivalently in supporting spatial information processing, spatial computation, spatial behaviors, and the like. And so that's really at the core of my basic work. And I've done a lot of, there's a lot of studies. I initially had them in here, but then it looked like it was going to maybe be a 3-hour talk, so I took them out. But there's a lot of behavioral work. We've done neuroimaging work. We have a large growing body of evidence that supports this argument. Next. Just 21. So I'm just going to skip through. This is just kind of some other possibilities besides amodality. And I argue for the third here. Next. All right, so the practical fallout of functional equivalence asks, okay, so can non-visual interfaces support the same performance as visually based displays? And so my research here involves issues like what is the critical information that should be given, what's the resolution it should be given at, what's the view depth, what are the the perspective that should be taken. Are you going to rip your body apart? Sorry. Sometimes does this in class. He grunts. Next slide. So much of my current research is dealing with information requirements and interface designed for use in indoor navigation systems. A lot of my focus is on indoor spaces because they provide particularly vexing issues, some particularly vexing problems compared to outdoor spaces. Stop. So three factors that make a difference or that make it challenging. First are environmental factors. So compared to outdoor, with outdoor navigation, you have global landmarks. You might look at a mountain or a tall building. You can use this to navigate. You have environmental regularity, like blocks. You have naming and numbering conventions. These are all very useful for localization and cognitive reference frames. It's just not true for indoors. We don't have namings of hallways. We have very local landmarks. So this makes it more difficult from an information standpoint. My interest is in trying to figure out, can we improve indoor navigation by providing better access to some of the navigationally relevant cues that help outdoors inside. Number two, we have technical challenges. So outdoor navigation is obviously benefit hugely from localization, automatic localization from GPS fixes, geocoding of almost everywhere in the world. We have these huge GIS databases of streets and landmarks and location-based services for everywhere. Again, this is not so for indoors. So indoor position fixing is not possible with GPS, or it's very ugly and noisy because of signal attenuation. Another big problem is just that there aren't indoor GIS or building information systems are not standardized. So the underlying data structures are not standardized. So yeah, there's always this prospect, and there's growing greater precision of AGPS and Wi-Fi tracking and inertial tracking and the like. And I think that probably this is a technical challenge that has enough big commercial interest that, involved that this is going to be solved. But right now, this is still a major problem. The third are behavioral differences. Again, just compared to outdoor travel, mostly because of the differences in information, you get different types of movement patterns, and more constrained movement patterns, often less efficient searches, and the like. Okay, so my work is dealing mostly with points 1 and 3, but I'm also doing something on point 2, which I'll talk about. And my goal is to develop interfaces for indoor navigation that have multiple applications and users. So, the non-visual systems are obviously geared initially toward relevance to blind and low vision navigation, but they're also relevant to a lot of the aging folks that we've talked about, or anyone navigating in the dark. So imagine an emergency response person that's coming and the power's out, military applications, just guidance for tourists, like a car-based system that someone inside wants verbal description. So it's kind of universal design principles. These are expected to work for lots of different types of people. So I'll quickly go through some of these projects. Some of them are more elaborate, or some of these are pretty early stage. Next. I've by far done the most work on what I call dynamically updated verbal descriptions. So these are messages that change with respect to the user's position and orientation in the space. And they also explain the geometry of the space. So this is different from a traditional use of spatial language. So when you're navigating, you talk about language, you're usually getting static descriptions like directions. Go down the street, take a left, go 5 blocks, what have you. These are all given up front, so they're not dynamic. They don't describe the description, and they're meant for just navigating routes. And so I'm interested in whether we can use these updated descriptions to support more complex spatial behaviors that are more natural that people do every day. Do free navigation, wayfinding, cognitive map development. Next. So I've run a lot of studies. I'm not going to talk about most of them on this. A lot of this was during my work here and then some after, looking at these dynamic verbal descriptions. The basic procedure is that you had people, and this was for most of the studies, you had people learning a space that they didn't know. They're blindfolded or they're blind, and they're freely moving around using these descriptions to describe the space. Some of them were in real buildings, and in that case they're being led by an experimenter because we didn't want people whacking into walls. Some of them were in virtual environments using what I call a virtual verbal display. So they're using keyboard navigation to get around. But however they're moving, they're getting verbal descriptions of what's around them. And their task is to try to cover the floor and to try to find some hidden targets that are in the floor and to build a cognitive map. And then at test, we bring them to the real floor. So if they're in a virtual world, they transfer to the real space. And we ask them if they can find routes between targets. So routes were never specified during learning, so they have to be able to be able to figure out these routes from the cognitive map that they've built up. Okay, next. So this is showing some test performance for a virtual verbal display. So they're learning in a virtual world with the language, and also from a visual display, which is the control condition here. And you see in the figure that route performance is almost the same for the verbal and visual display when you learn with spatialized audio, which I'll explain in a minute. And it's much worse, like 50% when you learn with just language description. So language is saying left, right, just like the traditional way that you might think about getting descriptions. Spatialized audio is hearing. In this case, it's hearing the hallway. So it's something as simple as if there's a hallway to your left, you hear it from the left ear, right? So you're getting some spatial information in the signal. And this data is a pretty simple thing to add, but these data are very clear. The importance of adding spatial information to the verbal displays makes a huge difference in how people learn the space. And so there's a lot of implications here to real-time navigation systems, not just for blind people, but even for car-based navigation systems. So if your Garmin or what have you said left out of the left speaker, these data suggest that, yeah, you're using vision too, but having that information would help people remember this a lot more. Also for elderly people, this seems like something would be very useful. Again, because you're it's a perceptual interface. You just hear it from the left. You don't have to think about what left means. All right, next. I think I'm going to go through this fairly quickly because we're running out of time. But again, this is looking at the advantage of spatialized audio, so hearing the signal from a specific place in space, distance and direction, versus just language. And we're doing this with cognitive load. So the idea is that if you have a perception, spatialized audio is perceptual. You hear something from the left, you don't have to process what left means. Because language is cognitively mediated, you have to think about what left means, and so that takes cognitive resources. So if you have a secondary task, which navigation often is, usually you're doing something else, it should be much worse with spatial language. And so we did this with what's called an end-back task, and they had to do a second task when they were doing it. Next slide, while they were navigating routes. And just quickly, these results, as we expected, showed that both for time and error, people were much better. There's initially when you start with a secondary task, both audio, spatialized audio, and language are bad, but then spatialized audio gets much better. It falls back to baseline, which is saying that it's not affected by the additional load, and language is. So again, this is particularly important for navigation systems because you're rarely doing it in a lab. You almost always have a secondary task. All right, next. This is work that I know is some stuff was started here, and I worked on a part of this project looking at magnetic guidance systems. So this is kind of getting at the technical component, the positioning component. This is being done with a Minnesota-based company. So just quickly, I don't want to get too much into the engineering component, but a building itself has certain magnetic anomalies based on the rebar and the different types of structure, steel structure. And you can use these anomalies as particular signatures, particular magnetic signatures about where you are in the building. And so if you map these and then link them to a database, as you're moving through the building, you can actually use these signatures to know where you are in the space. So this is showing a kind of a mock scenario of the system with the magnetic sensor. It's feeding into an iPhone app, which feeds to a headpiece, which is giving you verbal guidance. Next. So we did a little study with this in the Mall of America, which is obviously a very complicated building. And these data are showing sighted performance, people walking with the system, but they're using vision. So this is kind of the control condition. The system's telling them where to go, but they don't. They're telling them the route, but they're using vision to actually navigate the route. And their performance on doing this, there's one route shown here. There were a bunch of different routes that we used. The average was 180 seconds to do this. And then we have a blind group, so they're using the system real time, but they're traveling along with their dog or their cane. And they took about 196 seconds, which was not significantly different. And then we had a group that was unaided, so they were given the information up front, as if they were getting route information from a bystander, say, and they have to travel the route using that in memory. And they were 273 seconds, so it's significantly worse than both the others. And I don't have the error data here, but they also were much less likely to get to the end of the route. So preliminary efficacy data for the magnetic positioning approach. But what I think is important from my interest is that this also provides really important information about the importance of, or the efficacy of real-time systems as benefiting indoor navigation versus static systems where you're giving the route information up front. Next. This is just overlaying some plots. I'll move to the next one. So I'm going to quickly end here, just go through a couple of current studies that I'm doing that are in very preliminary stages, but I think are quite interesting. This one I'm particularly interested about, or excited about. It's called Vibro-Audio Map. And the project investigates if we can use the vibrations from, and they're coupled with audio signals, but essentially the vibrations from a smartphone to create building maps, which then you can let people, people can feel these maps to learn about the building without looking at the phone at all and without using any external technology. So essentially what's happening here is we're serving from an ArcGIS server a ripped down rendering of the building. And when the person feels these lines on the phone vibrates. It's just vibrating the battery vibration motor. And you'd say, well, that's not going to work. Certainly I did, because it vibrates the whole phone. But because you're touching it with one finger, you're getting very focal stimulation. It's amazing how much it feels like you're feeling one line. And so we're doing some preliminary work here, just looking at some kind of low-level things like what's the optimal vibration pattern, what line width do you need. But we have some good initial evidence that people can use these vibration patterns to learn a space, a map. And we're doing this offline at this point because we don't have positioning. But to be able to learn a map using these vibration patterns and then perform tasks that, the pointing tasks and recreation tasks that show that they've really learned this map through this phone. And I'm excited about this because it's a piece of technology that exists. This could be very easily implemented and widely used. Next. All right. I'll just go through two more then. So this slide is looking at auditory interfaces, again looking at spatialized audio. But again, we're trying to couple it to a smartphone. So using how can we learn about a room or a building using the smartphone, using spatialized audio? The problem is that in most cases, spatialized audio, you're tracking the head, and as you move your head, you hear where these things are. We're trying to see, because there's inertial sensors in the phone, if you move the phone around, and the phone is mediating how you're here, what you're pointing at is what you hear. Can you couple the hand registration with the head registration and use this as a way of learning about the space? In a way, that may sound like not that big a deal, but technically, it's a much easier way to implement. But perceptually, the question is, can people do this easily? And so we're just starting some work on that. Again, it's nice if this works because it could be done on off-the-shelf hardware. One more. This is a project I'm working on with a bunch of different people, but the goal here is to take a picture of a room, convert the image into a spatial form, and then generate natural language descriptions of this space. And so the reason why I think this is particularly interesting is that a lot of the work that I'm doing and that other people doing is looking at navigation. It's looking at getting from place to place, so kind of the network. But this is saying, what about when you actually get to the end node? How do you still need a description of that? How do you get a description of that? So like when I walked into my hotel last night, I wasn't exactly sure where the counter was, and it turns out I went and stood at a table for a little while. It kind of felt like the counter, but it wasn't. So if there was a way to get a description of the space in this automated way, that would be very useful. And this type of, we're working on just how to provide verbal descriptions of spaces. It turns out this is very hard. How do you actually get an automated description of a room? So if you have 10 people give a description of a space, you get 10 very different descriptions. So we're working on how to do this. And there's a lot of things like over there, this prepositional vague, which is very difficult to deal with. But these results are interesting to companies, to search companies like Google as well, because they'd love to have a way to be able to search and index images. Next. I won't go through this. This is actually a vision-based navigation, doing indoor navigation with a PDA that we're just starting. So I realize I've given kind of very high-level descriptions of some of these last projects, but they're all kind of in early stages. But that said, I still think that they provide at least the beginnings of viable solutions using a bunch of different modalities for accessing environmental information and providing navigational assistance, which is kind of the argument that I've been making through this whole talk. So I'm really excited about the potential benefit of these to a bunch of different users. I think there's a lot of benefit. Next. So here's some references and grants that have supported me, my students. And finally, next. So thanks. Yeah, I'm happy to take questions.
Thank you. If you remember, we have to use the mic for any questions. So anybody have any questions, bring the mic, or Sean will bring the mic from his end.
Okay. I actually have a couple of questions, Nick. One sort of philosophical, the other kind of technical. The idea of universal design is great, but people can come up with examples where a design feature that's helpful for one group might not be helpful for another. You mentioned the curb cuts. Sometimes people say that's actually makes it difficult for visually impaired people. There are other examples of sounds that might be helpful for visually impaired people might be a obstruction for others. So that's one question. How universal is universal design? And the other question is, for the spatialized language, what's the state of the art? I mean, how good are headphones, and can you buy stuff off the shelf that will really give you spatialized sound?
The first one's harder to tackle. Yeah, I mean, there's definitely issues with universal design because universality doesn't really exist. But in a lot of cases, some of the issues that you're bringing up can be dealt with through better design in general. So like, take for example the bumps, the tactile warnings. They used to be staggered. So you'd go across, but then anyone in a wheelchair or rollerblades or whatever couldn't get through them. So they realized, okay, we need to figure out ways to put these in columns so people can have a way through. That's not, that may not solve everything, but there's a lot of things where I think that through better consideration of the problems, you can come up with some answer. Yeah, there's not going to be one solution for all, but yeah, I mean, even I find that the APS that have these loud things in the middle, they're irritating. It's ambient, it's pollution in a way. But that's why I really like having these ones that are near the post, because it's a much localized. You can use it still directionally, but it's much less invasive. I'm sure there's people that still don't like those too, but I guess what I'm saying is I think there are lots of workarounds, certainly not to all things, but to a lot of these things. The state of the art for spatialized audio is, so there's two issues. Well, it depends on if you're doing it full-blown or you're doing head-related transfer functions and what have you. There's a lot of software that does this now, and there's some question, can you use a generic head, or do you actually need to model? The hardcore psychoacoustics people say you need to model the head. A lot of people say, have done experiments to show you don't need to. But I think the bigger issue at this point is just the tracking stuff. So you can get really high-end IMUs that will track, they'll do inertial tracking of your head, but that's not practical in a real time. The stuff on the phone right now, it's not really good enough yet. So like you get a lot of drift, you get a lot of error, but these sensors are becoming smaller and better and more integrated. So again, I think that's right now you still get a lot of noise, and because spatialized audio is really, to work well, it needs to be highly precise, and it's not perfect at this point. But that's again a technological solution that I think is certainly coming, just because you're seeing more and more uses of the same technology, accelerometers and gyros, in mobile technologies for totally different reasons, but they can be, dual used for this.
Thanks. There is one online. Are tactile maps universally usable, or are they limited to those who know Braille?
It's a great question. So first, there's no, you look at a map of, a geographic survey map. There's symbols. All the symbols are standardized. There's huge, lots of standardization. Tactile maps don't have any standards, so that's obviously a starting problem. So they're not universally usable in the sense that different people use different conventions. There's some push for that. You don't need to know Braille though, because it's just a lot of times, the symbols are. It's like on a print map. You don't necessarily need to be able to read the map. You need to be able to read to know what streets it is, per se, but you still can get an idea of the global structure of the map just by feeling it. So one advantage of or new use of tactile maps is augmenting them with audio. So if you put them on a touch display, you might not even need Braille at all. As soon as you touch the street, it gives you an audio message. Okay, that's Washington Avenue. And then you can add a lot more information from a database, give you the population of this town or what have you, because you're complementing it with audio information.
Any more? My example, as you were going through, you seemed to, it seemed to me that you talked about two kinds of things. One was information that was directed at forming a knowledge of the layout of a space, and other things that talked about obstacle avoidance and very local things. And do you differentiate when you approach a problem between those two kinds of issues, or are there many more?
I'd say the short answer is there's many more, and yes, I do differentiate, although I didn't really in this talk, because a lot of the things that I think relate to transportation and environmental awareness are these very local things, where in my research I'm more interested a lot of times in kind of the higher level. Can you actually do spatial updating? Can you do do you build some sort of knowledge structure of the space? So I think there are different ways to look at this, but from the standpoint of, I think, what are implementable solutions, these generally relate to things that are in the environment, that are much more local about obstacle detection, awareness of environmental features and the like.
One more question here? Yeah, well, two quick things. One first, a comment. The beginning piece you were sort of talking about with standards and guidelines and sort of the issue that there's not really being provided rationale to professionals and designers. I think that's critical, and I did see a note on there that you had sort of the situational immersion or a way to apply context to people who are working in design. I think we really need to encourage and develop tools and resources for that. Much of the mistakes and things that are happening needlessly, particularly in public rights-of-way, are related to people really trying to just look at standards without thinking of context. And I think if we just ramp that up a little bit more, we'd need less guidelines and we'd have better just design. And then I had a question. Just you showed an image of what was, I guess you called it the APS Crosswalk Map design. Is that a standard design, or I've not seen that before, and is that something that's being used in a community?
I've only seen one in Europe. I know there's companies that put them out. I have not seen them, and again, a lot of the work that I do is not at this level. So I was going from a lot of these things were coming out of things that I experienced and thought about as issues. So I don't know the distribution or the implementation base of these, but I know that these crosswalk tactile maps on the box have been used or used a lot more in Europe than in the U.S. I don't know where they're implemented here. I think that it really does make a huge difference, though, and it seems like something that's there's no electronics component to it. I mean, it's something that really could be done fairly easily.
Yeah, I think that's especially important also to be able to show that there's a median, given that some of the guidelines say not to use tactile strips with less than 6-foot medians, and that can be really important information.
Yeah, I agree.
Anyway, please join me in thanking Professor Giudice for his very interesting talk. This is the last in the series. Those of you who are not on any of our email lists who want to, we'll probably continue some of these seminars next semester on an ad hoc basis. They're only regularly scheduled in the fall semester. Spring semester, there might be a few more. So if you're interested in being on our email list, why don't you contact Sean Haig, and we'll be sure to add you to our list of announcements. Thank you all, and enjoy the rest of the winter.